Okay, on that clock, it's still 13 past, but on my watch, on this clock, and on my laptop, it's all 15 past. So what do you believe, right? What do you believe? I mean, I will go with these three. It's quarter past, so let's get started. First of all, Happy New Year to all of you. I'm very happy to see all of you and that you have all your fingers and everything, right? And that's, I hope you also didn't indulge too much in either alcohol or going to bed late or whatever your vice is. And I'm very happy that in this very first week of January 2024, you chose to be here. I have to say this is the first time I am here in the first week of January. It's the first time in my life that I attend either a lecture or actually even work. I'm 42 years old right now, and I've managed to always avoid this 1 week. But because Dr. Mohandet could only lecture the first half of the course, somebody had to lecture the second half, and well, yeah, that was me. So I had a choice, either to abandon you again, just like I did right before Christmas, and just pre-record things from the pleasant leisure of my workroom, or actually show up here. And I thought, hey, why not for the first time, right? I mean, that's actually do that. So yeah. Speaking of first times, it's the first time you see me lecturing, not just a recording. By the way, I mean, if Zoom can quickly respond if you can hear me, I mean, I see all the right icons lighting up, but if you can't, then let me know, then I can fiddle with this. As I normally have to start when I start lecturing here, normally this is EML, first lecture or something like this, I always have to explain that this lecture hall is a bit of a magical place. Why is it magical? Because every time I lecture here, something is different, broken, or it's always an adventure. It's always an adventure. So this time, some of you who were already here, I mean, you've noticed that my access card, which it expired, the old one, I got a new one, then it didn't work. I got a new one, it didn't work. I got a new one, and then another new one, and that finally worked before Christmas, right? I mean, that's during my break, I drove over and it worked. Right now, I did bleep, and it said, eh. Okay, that was number one. Number two, then, so in this cabinet, there's all the microphones and stuff, right, over which you can hear me. They were all blinking red. Red is not good, right? They should be blinking green. But, and it's not that my colleagues didn't put them in the charger, but I've got no idea what happened. So I had to exchange batteries. But then, while I was doing that, I mean, that's fine. I mean, then here you have 4 different microphones you can choose, right? I mean, that's, and the one that I now had functioning was microphone number 2. And on this screen, this is a touch screen, you can then press unmute. Doesn't do anything, it just stays muted. But, so in the end, I had to exchange again batteries to microphone 1, then to find out that actually that one does mute and unmute, it just doesn't show it. So wonderful world, right? Wonderful world. I mean, that's good. So now, lecture number 9, 2024. I don't have the date on the slides, this is new, but it's 4th of January. Let's get started. Let's get started. Today we're going to do something slightly different than, well, the first 8 lectures of EML. Because so far, you could have said, well, EML is a pretty lousy name for this course, right? I mean, that's, so elements, I mean, I think that everybody now understands what we mean by that, really the fundamental building blocks, right? I mean, machine learning, right? Now you also have a bit of a feeling for it. But if you remember from the first lecture and also the online lecture, we gave an overview of what machine learning consists of. And so far, 8 lectures long, we have only and exclusively been talking about supervised learning. We haven't been doing anything unsupervised, right? And this is just one branch of machine learning. So up till today, we should have called it elements of supervised machine learning. And actually, even after this lecture, there's going to be one more that is a bit unsupervised, but it is still a pretty apt name. So we provide you with really the basic building blocks of machine learning, but with a very strong focus, because we follow the book, on supervised learning. Now that I find a bit of a pity, given that my own research focus, and for a large part out of Cricamol as well, is actually on unsupervised stuff. So, but yeah, we need to do something. We need to lay some foundations, and then afterwards you can take even more exciting courses, or leave it for what it is. So, supervised versus unsupervised. Why is unsupervised easy? Both easier to lecture and easier to do. Well, we are given some features, x1, 2, 3, all the way up to p, and then we need to predict why. And we get a whole bunch of examples. And learning from examples is easy. You just given enough examples, then when you already know a whole bunch of techniques that can find the dependencies and somehow extract some signal from that. Now, in unsupervised learning, we are only given the features and a well-meant good luck. Your task is not pre-described. Your task is now to find some pattern, some structure, some cluster, some subgroups in this data. Try to find the hidden structure, but stress on hidden, right? I mean, it's not that I know what it is and I'm not going to tell you. That's the supervised case. It is hidden in the case. We don't know. Maybe there is something, maybe not. What can we do? So this is a very open-ended game where the target is really find something interesting about the data. What you could say, let me skip the rest. There's also paradigms that mix the two a little bit. But unsupervised learning is not just more challenging because, well, it's a bit more fuzzily defined. You don't know exactly what to do. It is also very difficult to assess the quality of the result of an unsupervised learning method. Because if it did its job and there was no segmentation fault and it returned something, then yeah, okay, well, how good is this something? You can't say, oh, let's calculate an accuracy, right? Let's generate or gather more data and see if we can predict if these people fall ill or develop side effects, or if we can protect a system better against attacks, right? No, it's more like it gives insight. It's very fuzzy. It doesn't mean that it can't be done. You can still use all sorts of techniques to figure out how much structure in unseen data can you explain away, but whether the result is truly useful, truly interesting, it's a bit like beauty. It's in the eye of the beholder. So we don't have the luxury of just test error. But there are big advantages to the whole unsupervised learning game. Namely, it is much, much, much easier to gather large amounts of data. Or in fact, data at all. Supervised learning, what we've been torturing with now for 8 weeks in a row, before the Christmas break, obviously, it's a bit make-believe. So in all the cases where we looked into, these are very artificial. Advertising budgets and revenue, okay, fine, right? I mean, in certain cases, sure, I mean, you give a certain cohort of patients a certain drug, and okay, well, there we can record, do they live, or how long do they live, or how happily do they live, right? Sure. But these are very compact settings, very overseeable. In many, many cases, it is very difficult, or even impossible, to get a label or labeled data. And now going back one slide, this is what these paradigms, we say these other paradigms, I gray this out. Whenever I gray something out on a slide, and I believe Crickable is the same thing, this means it is something that needs to be said, but it is not that important. You don't need to study it in great depth, right? It's more, you need to know there are paradigms beyond purely supervised and purely unsupervised, such as self-supervised. Self-supervised is the method behind, amongst others, ChatGPT, essentially. Right? I mean, that's some purists may disagree with me, but essentially ChatGPT is predicting from a bunch of words in its history, in its window that it's looking at, right? In the context, you could say, it predicts the most likely next word. And then it generates this one. And it generates then the next one, given the now updated window, and so on and so forth. And that way, all of a sudden, from an unsupervised setting where you just can prompt whatever you want, and it's very difficult to now say, like, is this now exactly correct, yes or no, right? You can all of a sudden train this very simple language model if you just have a lot of text. We just start from somewhere, predict the next word, we shift the window a little bit, we predict the next word, and so on and so forth. And we can now compute an accuracy, or how close are we in terms of distributions, for how close is the predicted word to the actual word in the text that it should have predicted. And that is a bit of a hack, right? It's technically ChatGPT is unsupervised because it's not trained in like, this is the right answer, that is the wrong answer. It just predicts the next word. So there is this in-between realm of self-supervised and semi-supervised and whatnot. Now, big advantage when you have lots of this unlabeled data or only implicit labeled data, if you have a lot of it, then there's a lot to discover, right? One of the key problems that we've seen so far, if we do also linear regression, logistic regression, and all their dear friends, you need quite a lot of data. Otherwise, you can't estimate your coefficients quite well. And then things become insignificant, and both on the output and as well as on the coefficients. And what do? You need more data. If you don't have it, or it's too expensive to obtain, unsupervised is the only thing you can do. Now, the other big advantage is that I write here the most interesting tasks. Plenty of people will strongly object to that, but they are unsupervised in nature. Namely, almost every task in science, we gather a lot of data, be it in chemistry, be it in physics, be it in bio, be it in social sciences, humanities, and so on and so forth, right? We want to figure out, is there some pattern going on? These are all exploratory in nature. These are all focused on discovery. And these are often types of questions where it's indeed fuzzily defined. It's more like, well, if you can find me, I mean, I don't know what I'm looking for, but I will be able to tell it when I see it, right? You know this expression. Well, how do you do this? You can do this with unsupervised machine learning. That's what we're going to discuss, a very small sliver of techniques today. Some examples of what you could want to do, group genomic signatures of patients and sub-patients, so subclasses of cancers or whatnot. You can characterize, I mean, if you want to make money, I mean, shoppers for browsing and purchasing habits. If you apply this to time series, you can actually discover trends in the stock market, and you can exploit them for a very short amount of time until somebody else finds the same pattern and the market becomes too chaotic. And this is actually, so until not so long ago, I would have said, okay, this is nonsense. This doesn't work anymore. But very recently, I was chatting with somebody who did make well, they didn't buy a yacht out of their money, which is smart, right? Because I don't know if you know the expression that when it comes to boats, anybody who owns a boat, right? I mean, there's 2 days where they were owning a boat that they're happy. The day that they bought it and the day they sold it. All the days in between are just miserable because boats cost a shit ton of money to maintain, and it's just a headache. But what I've always said, if you can predict the stock market, you can make money, show me your boat, right? I mean, that's or a car. I mean, if it's fancy enough, I also buy it. But I've never seen somebody show their car or their boat. Okay, it's not going to happen. Recently, somebody could show me that, well, they could buy the boat. They could buy the boat by using very simple techniques, very similar to what you've now been taught in EML, to basically predict the crypto markets. And, well, all those tricks have now been taken up in the market, so I'm sorry, right? You need to be smarter than what they applied, but all of this is useful. Movies, Netflix, Disney Plus, all these online subscription models, all these recommendations. It is not a supervised task, right? I mean, what are those movies that are most likely to be liked by you? Those are the ones that they want to recommend, because then they hook you into their system and your subscription is going to be continued and whatnot. These are all tasks that primarily rely on unsupervised techniques. One aspect of unsupervised learning, and we're diving a little bit in this direction, that's why I show this, is visual data exploration. It's not quite my forte, but it is a very richly studied domain, and there is a lot of interesting things that have come out of there. And the most recent advances, well, okay, they're nice, but if you simply think about data, one-dimensional data, I'm not going to show you how to visualize these things, because most of these things you will already know, and depending on what the tutors choose to include in the tutorial, they will show you a number of things. But what you can already do, you can compute some summary statistics, right? If you have just one column of data, you can compute a mean, a mode, the median, quartiles. I mean, then you have, before you know it, if you combine this, you have a box plot. That gives you already quite some insight in how individual attributes are distributed. If you're really interested in how the distribution of the data is, well, you can look at histograms. Basically, bin your data, for example, ages, right? In bins of, let's say, 5 years, and then contiguously, and just count how many people fall in what bin, and then you have a nice visualization of the distribution of ages. You have things like dots and B-swarm plots, kernel density estimation, and violin plots. Those are all very useful. I'm not going to dive into that too much. But they're all focused on one-dimensional visualizations. Amazing, but the real magic to be discovered from data is if you look in higher dimensions. So 2D scatter plots are already much better. So here you have three different types of plots. You have a scatter plot, but not the scatter plot like you normally just plot it if you do this yourself using GNU plot, if you use Python or whatnot. But, as you can see in this one, and I like this particularly style of plotting, you have these light gray dots. These are basically the data points. And the moment that they start to overlay, then they become darker and darker and darker. And it is this opacity trick that actually gives you some insight in, well, how dense is the data where, right? So it gives you an overview of the 2D density, not just where are points, but really of the density. When I said that visualization research, visual data exploration research, interesting things, but this is one of the outcomes. This is a good way to plot things. But, here we have a density plot where we adjust the, basically it's a kernel density estimate underlying, and the color becomes hotter, so to speak. The more dense we estimate is the probability, or the higher the probability of a data point living there. Here we have a hexagon plot. Hexagon plots, you take your space and you plot it into hexagons, basically these a beehive type of dots. And then you just color them according to the density that your KDE says that should live there. Three different ways of visualizing exactly the same data. And, well, you tell me which is the best one. I mean, if you have a favorite, good. But there is not really anything to be said like which one is now intrinsically best, right? Again, beauty is in the eye of the beholder. Now, let's move away from density plots. Density plots, nice. Where do points tend to live? But the moment we go to really higher dimensional data, density plots rapidly use their function. Higher order densities are essentially meaningless. It's a strong statement, and I can back it up a bit later in the lecture. But for now, just trust me. Let's start with trying to visualize data in higher dimensions. Here I have a three-dimensional plot, right? Because this is, I presume that all of us in the room here can interpret a three-dimensional plot. If I would have shown a 4 or 5 or 6-dimensional plot, it would have been much more difficult, right? But suppose that this is really, this is essentially beyond us, right? This is just a big table and we have no idea, right? I mean, and we would like to now to plot it down to 2 dimensions. We would like this 2-dimensional plot to show us the main structure of the data. That is the task which we'll be studying for the next, well, not hour and a half, but hour and a bit. So, just to make sure we're all on the same page, double helix, right? That, you can see that this one here, the blue strand starts over here, then swoopity, 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 and the red one starts over here, and it follows. But now, PCA, which you already know, and I'm going to be discussing it in a little bit more detail, is one of the techniques that you can use to project high-dimensional data, let's agree, 3 dimensions is high, to, well, to a lower set of dimensions. But, what we can do, we can discover the first principal component, and then the second principal component, right? And you will recall from earlier lectures that the first principal component is that direction in the data that explains the most variance, right? So basically, if you have to predict with one coordinate as close as possible for each data point of your data where it lives, the direction of highest variance, that's the one that you want, right? I explain this mostly to myself because I always find this a bit confusing that you want the direction of highest variance and not lowest variance. But okay, so after we found the direction of highest variance, we reproject the data and we do it again. And then we have 2 dimensions, the first and second principal component, and we can plot the data. And it would look, in this particular case, like this. Is this a good low-dimensional embedding? Low-dimensional embedding is just a fancy word that we use these days for 2-dimensional reduction, such that we can visualize it. Is this good? You shake your head and you raise your hand. So I'm very confused. You shake your head. Why isn't it good? You can't separate it. What can't you separate? Okay, yes. So basically the 2 lines, the 2 colors, right? Or the 2 classes. That's what you mean? Is it the red and the blue? Yeah. Did you have a different or a similar? Yeah. no, true, yes. Indeed, I mean, if I were to task any of you to reconstruct the left data based on the right, you would be up the proverbial shit creek and you would be in dire need of a paddle. It's impossible, right? But at the same time, we are bound to always lose some information. Right? If we go from 3 dimensions to 2 dimensions, only if the third dimension is completely just flat, right, basically doesn't exist, okay, then we don't lose any information. But otherwise, you're bound to lose something. And you're absolutely right. I mean, we can't really separate the 2 strands. And I would say that the fact that here the blue one starts higher and then the red one starts, do you see this in the right-hand side? Not really, right? Not really. Going a little bit further on your remark, I mean, on the right-hand plot, it seems that they're connected. It seems that there's somehow a loop, right, where just it switches colors. It's also not true, right? I mean, so yeah, so PCA is nice, right, nice starting point, and in practice quite useful. We'll see this much later. But salmon mapping, or multidimensional scaling, was a proposal, late 60s, 70s. I mean, a number of people worked on it from different angles. And if you apply this, you get this particular plot. It's already a bit better, perhaps. Is there anything else to be commented here that we haven't said already? Sir? Mm-hmm. Yeah. Well, that's a fair point. A fair point. I mean, going a little bit, I mean, skipping ahead a little bit to later in the lecture. So what salmon mapping or multidimensional scaling attempts is not to explain the variance in the data, but actually tries to maintain the distances between points. So the distances on the left-hand side in 3 dimensions are captured maximally well on the right-hand side. And that's exactly what you see here, right? With the blue strand and the red strand, I mean, they have here a distance and they maintain this distance. So you can actually see much better that there are 2 strands. They still crisscross, right? I mean, but you can see this better than in the PCA plot, because PCA doesn't have a notion of distances. It only cares about variance, right? So this one is, in a way, a bit better if you care about distances. This already shows that, well, if you don't know that you care about distance in the data, or that you should care about distances in the data, or maybe you should care about the variances in your data, I mean, yeah, the one or the other technique is better, right? Or better said, they're just different. Good. This is the result of TISNE, T-distributed SNE, stochastic neighborhood embedding. I like this one personally a lot, because it does separate the strands very, very well, right? But I'm pretty certain that we can also say something negative about these. Who can say something, well, negative or critical? You in the red shirt. Exactly. The structure of the plot, yeah, that is gone. That is gone. But it does show, much better than the others, that there are 2 strands at equidistance, and that the one starts a bit earlier than the other. That's what it does show, right? And, well, the others, they fail more miserably at that. So now we have 3 techniques, each with, well, let's say 50 years in between, I mean, plus minus. So it's visualization and embeddings is a slow, or was a slow-moving field. In recent years, it moves very rapidly. We're going to be walking through these 3 techniques one by one. I'll show you how the math works behind it, where their strengths lay, and where they break down. Before we go there, why do we even need them, right? I mean, well, first of all, if I give you a 4, 5, 6, whatever, 200 dimensional, or let's take genetic data, right? I mean, 20,000 genes that we know, right? Or you take all main loci, and you look at data of hundreds of thousands, millions of columns. Good luck visualizing that. Good luck seeing something. Right? Good luck making use of the very strong pattern recognition engine that you have in your head. So high dimensional data is hard to visualize. If you have some, well, not exceptionally high dimensional data, but there are strong correlations between the attributes. Collinearity, right? I mean, you've seen this already. I mean, that can screw up many an algorithm. Actually, most algorithms will spit out something random. Sometimes they will use the one attribute and say the other one is uninteresting. Sometimes they will do the opposite. Sometimes they will ignore both because they can be explained by each other, and I don't like that. Maybe it does include both. You don't really know what you will get. So that's not great. Now, another point, I grade this out because this is an answer I do not like to hear at an exam because it's sort of the easy way out, right? I'm not going to count it wrong, right? I mean, if I ask you what are the challenges with high-dimensional data, but please write something in addition, right? I mean, please do it for me. Of course, if you have very high-dimensional data, computation is going to become easier, right? If you want to compute the similarity matrix between attributes, then yeah, well, if you have 2 attributes or you have 2 billion, it makes a difference, right? And that, if you now do a squared computation on that. The real reason why nobody likes high-dimensional data is the curse of dimensionality. It's a rather dramatic name for a also quite dramatic phenomenon. It's a bit counterintuitive the first time you encounter it, right? If you never really thought about high-dimensional data. Because on the one hand, hey, the more the merrier, right? Measure everything relevant, right? Or make sure you measure everything relevant. And if you have a few additional features, who gives a damn, right? We'll figure out which ones work. However, as all of you are already experts, it's not that easy because you need a lot of data in order to tune all those coefficients to determine if a feature is useful, yes or no, right? You've seen in feature selection, subset selection, right? I mean, that's if you just start with one and then the other. If I give you literally 1 billion features, yeah, maybe you can do something, but that's computationally going to be very hefty. Plus, if you need, now let's say 10 attributes that together can explain something, yeah, and you do this just one by one, and maybe you just by the lack of data, your algorithm gets confused, and it doesn't take attribute 2 after choosing attribute 1, but it likes attribute 50 better, and 50 already explains a little bit 3 away, then before you know it, you end up with a basket full of deplorable features that you can't really predict anything well with. Bottom line is that with more attributes, you need more data, and effectively, from a sample complexity perspective, you need exponentially more data. And that is scary, right? This also holds for the supervised case, right? So just adding more features does not necessarily make your life better, right? But, red shirt, what's your name? Because I don't want to call you red shirt all the time. Sorry? Ben. Essentially, so the simplest way of thinking about it, so in continuous valued land, I mean, it's a bit difficult. Just imagine we live in binary land, right? We live in Boolean land. And I give you, let's say 2 features, right? And that's how many data points will you need to get a good estimate of how often each combination happens? Well, there's 4 possible combinations, right? 0, 0, and so on and so forth, right? Not going to list them all. So you will need, I don't know, let's say 40 data. I'm just making this up, right? I mean, the exact number. I mean, that doesn't really matter. I mean, in the big O notation. So let's say 40 data points, right? And then for those 40 data, then you can estimate what is the probability of seeing a 0, 0, 0, 1, and so on and so forth, right? I mean, now, I grant you, right, because it's New Year's, a third feature. Is 40 data points now enough to properly estimate the probability of 0, 0, 0, 0, 0, 1, and so on and so forth? No. How much more data do you need? Well, we went from 4 possible combinations to 8. If I give you another feature, and so on and so forth. That's where the exponential comes from. Of course, in continuous valued land, but the idea remains the same, right? Yeah, good. Okay. So you need a lot of data. Does this mean that you always need really a metric shit ton of data? No. That's the bottom point. We'll get there in a second. One other thing, what is really the curse of dimensionality known for, is that if I give you more and more and more features, then the distances between points, so basically how different are you, Ben, from, what is your name with the orange shirt? Nota? Jota. Was it correctly pronounced? Okay, good, close enough. I mean, in the break, you can tell me how to properly. Well, you are quite close to each other, in distance sense, right? There's two people in between. I'm not going to ask your names. Don't be, not yet. But you have much more hair than Ben does, right? So okay, so that discounts a little bit. Well, and I don't know how tall you are, right? And I don't know what shoe size you have, but if I would ask you to stand up, then I can measure how tall you are, and then we can also see how many fingers do you have, and we can measure more and more things. The more and more things we measure, the more similar the two of you will start to appear compared to everybody else. Because there's only a few aspects in which are relevant that tell the two of you apart, right? That is not just between the two of you, that is within any data set. So if you have more features, then on expectation, unless the low dimensional manifold, that I will speak about in a second, is extremely low dimensional, actually that even doesn't even matter in this case, all the additional meaningless features, right? I mean, on all the meaningless features, every point, every pair between you are approximately, on expectation, equally different, right? It's only on the relevant features where, well, you are then closer, respectively, further away. So that you can already see, if I give you now more and more and more meaningless features, the overall distance, the similarity between two arbitrary points, starts to become smaller, 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 smaller. And this happens really rapidly. Right? A few years ago, and we're talking 10, 15 years ago, so perhaps a bit more than a few, if you were talking about clustering high-dimensional data, you were talking about clustering data of 10 features. That was already like, okay, just don't let friends do that, right? And that friends do not let friends do that. Now, the relevant features, right? Amount of hair, shirt color, right? Something like that. That's what you call the low-dimensional manifold. Most data sets, the actual action is on a low-dimensional manifold, right? All the rest of the features are meaningless, right? We can ignore them. We just don't know which ones we can ignore. So discovering what is this low-dimensional manifold, that is the name of the game, right? Just mathematical wording, right? We basically want to find the mechanism, right? I mean, that's the relevant mechanism. So our goal right now, today, is reduce the dimensionality of your data to a much lower dimensional data set, either by picking and choosing a number of features, right? That's one strategy. You already know how to do this. We're not going to repeat that today. We're now going to try to take this very high dimensional data and project it down onto 1, 2, 3, a handful of features that are highly informative. And in the process of creating these new features, well, we basically ignore all the fluff that can be ignored. So essentially, we want to uncover the intrinsic dimensionality of the data. How much exchange is truly going on? Good. I normally always lecture with a bottle of Club Mate. And first time I had it was here in Germany. This roughly 10, actually, I think it's 10 years ago. 10 years ago I started teaching here. It tastes like cardboard. The first sip, I was like, what is this? Right. The second sip, because somehow, I don't know, I wanted to finish the bottle. Like, okay, well, it's not so bad, right? Apparently I'm a cardboard man. And the third mean, then I was hooked. And ever since, every lecture, except for this one, I lecture with a bottle of Club Mate. Now, last year, I was also the same time slot for EML, and I noticed that if you sip an entire bottle of Club Mate between 4 and 6, it does not positively affect my sleep patterns. So I decided to trick myself, and something that is also yellow and also cold and also a bit sweetish. So let's see if Apfelschorle also does the trick, right? But, if from now on the lecture quality really goes down, I'm sorry, right? That's, I apologize, and next time I'll drink Club Mate again. Good. Let's meet our three friends, PCA, Salmon, and Disney. First, PCA. Simple example, population, advertising, and basically well, this is just the data we have, right? I mean, that's so in how many locations did we, with what population did we advertise how much? I mean, note we're not interested in predicting something, right? And that is just to see what are the correlations essentially. Now, it's of course stupid to really try to project down this data, right? This is already two-dimensional. We can already see the trends, right? I mean, this is exactly why didactically this is a good example. Because if I were to ask any of you, what is the direction of maximum variance, then I hope that everybody would say, well, if it would not be drawn, they would hopefully say, okay, this direction, and it's just drawn, you would say, hey, the solid line. Whoa, okay, something really weird is happening here. Okay, good. Let's not touch it. Good. That's the direction of maximum variance, right? Let me repeat what I said earlier. It's that direction that if in one coordinate you need to give the maximum information, where does a point live? There you are, right? That's the direction. On that slope, you can best predict it. The dotted line, orthogonal to it, that is that direction that then afterwards explains the most variance. It needs to be orthogonal, because if it's not orthogonal, then yeah, it basically you're losing explanatory power, because the black line already explained all of that variance away. Essentially, principal components define a new coordinate system. They rotate your data, right? It's what you have over here. And that allows us to then also replot the data according to this coordinate system. And there we are. That's exactly what we're going to be doing, right? On the first principal component, this is basically what these points come down to, right? So this is also what you're trying to find, to come back to this direction of maximum variance, to try to find a line in which you can really spread them out maximally, right? That's effectively what is happening. Good. Yeah. Okay, the orthogonality I already discussed, and otherwise you're just losing explanatory power. So another way of thinking about PCA is that you iteratively try to find that direction that minimizes the sum of squared distances. That's the dashed lines that I painstakingly drew. I mean, some people take vacation, some people draw lines. And what we're now after is essentially that line that is closest to all observations, right? Note that this is not the same line that you would get if you do linear regression, right? It kind of feels the same, because there we're also trying to minimize something and follow the trend. And it's almost, but not quite. Almost, but not quite. First of all, we're not really doing regression here, mind you, right? Now, actually, can somebody tell me what is the difference? Ben? Exactly. Yes. So to repeat for everybody and also on Zoom, in linear regression, we basically look at trying to minimize the vertical distances, right? Basically, if you were to predict based on population 30 by this line, then, well, how far are you off, right? And now we do it perpendicular to the line, because, well, you want to explain the variance, right? I mean, how far away from the line is it per se? And of course, that you have to measure the right way, otherwise you're cheating yourself. But, good job. Formally, there's different ways of computing a PCA, principal component analysis, and the principal components. I mean, you can do it, a bit through a detour through the SVD. Essentially, what we're trying to do is that the first principal component, which we define as Z1, Z we typically use for a latent variable. It's essentially a variable in the data that, well, it's hidden in the data. It is kind of there, but not really, if you know what I mean, right? I mean, otherwise it would just be XQ or whatever. I mean, but this direction of maximum variance, it lives in the data in a way, right? But we just haven't measured it explicitly properly. That's why we call it Z. Now, the first principal component, we go over every feature from JS1 up to P. We have some magic coefficient, right, for that particular feature. The one that is corresponds to the one of the principal component. And what we're trying to do here, well, it's just what is the distance to the mean of that particular feature. Because the moment that we can, we want to basically predict everything as well as possible, but under this distance and not the per prediction. And then we get a bunch of coefficients, I mean phi 1, 1 for x1, phi 1, 2 for x2, or 2, 1, sorry, for x2, and so on and so forth. Okay, and what the mean is, you know, right? That's not so exciting. Now, I should have actually hit this and then just ask you. But okay, now I already gave it away. We require that these coefficients, they need to sum up to 1. This is just to make sure that there's a unique solution, right? Otherwise, I mean, we can come up with arbitrarily many, right? And that they would just be arbitrarily scaled. And okay, we need to have one that we can look at, right? Let me allow myself a small aside. I personally am a big fan of deterministic data analysis algorithms, deterministic machine learning algorithms. It's one of the reasons why I'm not a big fan of neural networks. Neural networks are a little bit too neurotic for my taste. What do I mean by that? Well, I actually mean many things at once. But primarily, you tend to start with a random initialization. You use random batches of data, and well, you add a few more times random, so it's a very stochastic algorithm. And essentially, if you were to run it, right, I don't know your name yet, but I'm going to figure it out. Or if Ben runs it, or if you run it, all three of you will get a different outcome. And they may be qualitatively very similar, right? You may get very similar error rates. It might be at completely different. It may be that yours predicts super well, Ben's sucks, and yours is okay, right? Or all the way around, right? I mean, and it's very difficult to tell how, what, and why. I don't like that. I don't like that. PCA, because of the deterministic nature, is something that I do like, even if it's not the ultimate algorithm. But if any of us runs it on the same data set, and we don't use a buggy implementation, we get the same outcome. And that is very pleasant. Yes? For what? It doesn't exist. I mean, return 42. I think that is the ultimate algorithm, right? I just don't know for what task yet. And that, no, there does not exist one ultimate algorithm. I mean, well, in very specific cases, if we know that, let's say, for sorting, right? I mean, even there, actually, even for sorting, even for something as simple as sorting, it really depends. Does it fit into memory? Are you getting additional points, yes or no, right? I mean, that's how badly doesn't fit into memory, right? And that if you're really interested in sorting, let's say, Google data cloud type of data, yeah, you don't want to use standard quicksort or merge sort, right? And you don't want to use a standard out-of-memory version of that. Right? This is still an active field of research. How do we do this best? As crazy as it is. If you want to do simple lookups, right, even if you make it more simple. If you want to do, you have a very large collection of data and you want to look up, right, I mean, that's, I want to query that who in my database, I mean, that has more hair than Jota. I'm still very uncertain about your name, and that's so that makes me very skittish. Anyway, I would like to find this in my data, right? I mean, that's sure that is solved, right? Databases are boring. That is solved in the 60s. There was very recently, because of the MPI celebrating its 33rd birthday or founding day, top researcher in database research presented a new algorithm that beats the state of the art by a large margin, and it includes some standard B-tree stuff and a bit of this and a bit of that and a bunch of machine learning, and they can now find much quicker if there's anybody in the data with more hair, yes or no. But so even for something as simple as looking up if something exists in the data, there is not an ultimate algorithm. So, yeah, I don't know. Good, let's continue. Coefficients need to sum up to 1, just to make sure we have one unique solution, and it does not limit us in any which way, right? And let that be clear. Now we want to find those coefficients such that overall we maximize the variance, minimize those distances, and there we are, right? I mean, this is doable. I mean, it's actually quite simple. Essentially, what you have coefficients for here. Actually, yeah, I was already thinking. I mean, so the data points. Okay, yes. No, this is why there's no square. Okay, good. So for each row of the data points, this is why then you have your square. Good. This is just linear algebra. Ben. There is, and I'm not 100% certain if this is now in the homework sheet or not. So I'm not going to answer this now. That's not to torture you, but I mean, well, mostly not to torture myself and my tutors. Yes. It is a line. It's a line. Yeah, it's a line. this we go. We'll see this in a little bit, because this is by definition, right? That essentially PCA is just a linear projection, right? I mean, basically you transform your data linearly based on the features you have, and this is by definition. This keeps everything simple. You could say this is a close cousin to linear regression. That's essentially what it is, right? With this flip-flop of these errors. And a lot of the machinery for how to compute these things then remains the same, and we can compute all sorts of things very nicely. Making it nonlinear is an active field of study, and how to do this properly. So maybe I say something later on, but I don't want to go off script too much, because otherwise I will not be able to finish the lecture like even by a long shot. So, quick example on the advertising population data, just by doing the magic we saw. What we see is that, hey, first coefficient 0.839, that's the difference, I mean, basically from the mean from the population, and 0.54. Okay, these coefficients we call them the component loadings. I'll show you on the next slide, I mean, how those connect. You can, if you stare long enough about this and even think, and thinking is then advised, out of every linear combination, population and advertising in this particular case, where this holds, the first principal component is the highest variance, or I mean, it has the highest variance, but this expression is the maximum. But, at the same time, closer to the data. So this is your question, right? And traditionally, this is one of the homeworks. Show this, but I do allow my TA some freedom to include it, yes or no. I mean, also, given how many of you love proving facts, right? I mean, that's not all of you do this equally much. So hence we flip it in, flip it out. So if it's not included in the homework, I'll have to check, right? Then I will either ask the tutors to explain it in the tutorials, or maybe in the next lecture that will include this. After we found the first principal component, the black line, we can do the same thing with the other, and there we are. But there you see something weird. And hey, wait a second, 0.544, this I had over here, and because it's orthogonal, right? And that's basically what you get when you have two-dimensional data. I mean, if I were now to ask, okay, compute now the third principal component, right? I mean, that's then return 42 is the ultimate algorithm, because I mean, with two-dimensional data, you can only project it, you can only discover two principal components. There's simply not a third one, right? It would be flat, right? I mean, making it orthogonal to both the first and the second principal component means that we just have a zero factor, and it's meaningless. On some other data, this is arrests data, or I mean, crime data from the 1973. I thought it was late 70s in the US. Statistics per state. I wanted to say Bundesland, but I mean they call them states. And if you now would like to gain some insight, okay, what are the dependencies between types of crimes or amounts of crimes and so on and so forth, right, in these different states, we can hardly plot murder, assault, urban population, rape numbers, and all sorts of other horrible features. I mean, and then just look at it, right? I mean that. But if you compute the first two principal components, then you get a picture like you have over there. Now, what we then have for the first principal component, we get these values. You see that for murder, it's 0.5, for assault, 0.58, for urban population, it's 0.78, and so on and so forth. So these are the loading factors, right? So this is really the direction of the first principal component. So essentially, in the original data, what is the direction of this? And then we have the other, so over the two principal components, but per feature, this is the projection of that feature onto the first two principal components, right? So how affine are they? But, what you can see there, let's focus first actually on the second principal component, because it's most outspoken. You see here minus 0.4, minus 0.2, this is 0.16, right? So these are low numbers, right? So essentially, the second principal component, that direction, right? So those features, murder, assault, rape, are not so important for the second principal component. 0.87, right, this one, so urban population, this is a major contributor to the variance of the second principal component. Now, the moment that you now see how you can interpret these things, you can also interpret this first principal component, and you see that the three actual crime statistics are very important, and the urban population, the number of people living there, much less so. That's not zero, right? And you can also see that the angles of those three crime types they're quite similar in the data compared to urban population. So what we there see is that, well, on the right-hand side, you have quite violent states. And here at the top, you have then more populous states, less populous states, but that doesn't correlate specifically with the crimes. So it gives you some insight, right? I mean, that's, if this is anything that anybody finds truly interesting, that remains to be seen, but it doesn't really matter. Good. So some insights. First principal component, crime rate. Second is urbanization. Okay, we learned something about the data, right? This is how we can explain the data. Now we go to the interpretations. And now we also go a little bit to the question that was asked earlier. Is it okay, just hold your horses? Let's walk through them. There's three interpretations that I want to walk you through. First one, principal components are the directions of highest variance of the data. Well, nobody's going to be shocked there because this is how we defined them, right? And that's so principal component score of an input. It's projection onto the loading vector, and then we see, okay, well, how affine is it? And that, second interpretation minimizes sum of square distances. So close to the linear regression interpretation. So the second principal component is essentially the residual of the first one, because you want to explain maximally what, so you want to get even closer. Now, that makes the principal component hyperplane and affine subspace, such that all the distance, basically, it's you want to try to find that plane in your data, right? That's sort of, if you look at the first two principal components, that plane in the data, that is closest to all the data points, which is exactly what I have drawn there on the right-hand side, or I didn't draw it, but I show it. There's also a third interpretation, namely principal component analysis finds a linear transformation into a new coordinate system where the data is linearly uncorrelated. That comes to your question, can we make it nonlinear, right? Can we make it polynomial? Yeah, I mean, in theory, you can redefine it, but then you lose this and lots of other nice properties you don't want to. You might say, okay, well, hey, the first two I could kind of see from this picture maybe, if I squint, look to the hairs of my eyes, but this third one, I got you. If you now plot the data onto the first two principal components here, and also if you think about the previous examples, I mean, if you were now forced by me or by somebody else to fit a linear model between these two principal components, I mean, yeah, no, right? There's essentially nothing left, which makes total sense because the first principal component explains maximum variance, the second one, the variance orthogonal to that, right? So you break down really any possible correlation. You generate essentially maximally uncorrelated in terms of linear dependencies on the input features. You break down anything that can already be explained. You find the principal components, those two coordinates, right? That, or more if you go for more, of course, that by which you can break the linear correlations maximally. You explain away as much as you can. It doesn't mean that you get nonsense output, right? But there's just linearly nothing to be explained anymore. Good. And if you would make this now nonlinear, the entire thing, then yeah, okay, then maybe you get something, but I don't know what it then means. How do you choose the number of principal components? I don't know if Krikamol did the same thing as I always do, but cross-validation, 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 right? So we can also just use cross-validation. I mean, that's for essentially any parameter, any choice, any algorithm, any method that we've discussed in EML. And if you're like, I don't know how to choose it, right? I mean, I don't have access to an expert who tells me, or an oracle that tells me 42, just use cross-validation, right? No, it's not ultimate by itself. But if you need to make a good and data-informed choice, then yeah, it's a very good, but it's not ultimate, not ultimate. I mean, we've seen that, right? How it can break down. So no, I'm sorry, I have to depot. The moment we encounter an ultimate algorithm, I will let you know. Good. Yeah, if you use PCA for visualization, and of course 2 or 3 dimensions, right? That is basically where you should stop. I mean, fourth dimension, okay, you can create sort of perhaps a data movie, but it gets very tricky. And beyond that, we don't know how to visualize, right? But, I have the feeling you want to ask a question, Ben. Oh, yes. So you're on the right track. So let's measure the amount of variance explained, right? And that's the degrees of freedom. Right? So, and this is amount of variance explained, right? And degrees of freedom is now number of principal components, right? That's 1, 2, 3, and so on, all the way up to p, right? I mean, more than p doesn't make sense. How do you think, right? So this is the plot where we start with one principal component, right? We start somewhere over here. How do you expect that the plot would go? Probably goes down, right? Because we explained more and more and more. And one moment, it will start to flatten out. Yeah? So there you have your answer, right? I mean, that's essentially cross-validation allows you to find the, a bit like in what's the other method? The elbow method, right? I mean, we had a number of these model selection techniques. So this is how you can tune it. No, they're not nonsensical. I mean, that's so. This is a tricky. It's a good question. It's a tricky question to answer properly. It's a bit of a matter of philosophy, or what are you after? So here, what you're specifically after, right? I mean, or this is an example, is we want to stay really close to the data, right? I mean, hence principal components, simple linear algebra, right? I mean, that so we don't project it into infinite spaces, right? I mean, through some kernel, right? I mean, that we project it through some kernel. We have a very strictly defined set of operations what we allow on the data, right? I mean, that and you can interpret what PCA does through one very specific kernel, but you don't want to open up the whole bag of tricks that the kernel trick essentially here, right? Why? Because the output it really matters to us. We want to be able to look at it and interpret it in terms of what does it mean on the data. And the moment that you start to use like kernel tricks properly, right? And that then essentially you open Pandora's box and fantastic things come out, right? But the interpretability generally suffers. And there I can say pretty much, I mean, this has to be the mantra of this like open topic for research on how to generalize approaches like these such that you can get efficient computation and freedom of different kernels, such that you, for example, can go to nonlinear projections, right? I mean, that by using an RBF kernel or whatnot. But here, the whole idea of PCA and friends is really you want to do something simple because you want something that is strictly interpretable at the end. Yeah? Good. Okay. Yes. We can process the data. Yeah, okay, well, maximum, so how much variance? So you want to find how many principal components such that, let's say, 90% of the variance of your data is explained, right? And you just say the last 10%, okay, that is noise, or 99%, right? This is the question that Ben just asked. And then you can figure out, okay, well, I just either set it to 99% needs to be explained, and maybe that can be done with 3 principal components. Maybe you need 50, right? I mean, that's maybe you need exactly P, as many features as you already had, right? And that it is impossible to explain 99% of the variance in less than P principal components. Yeah, this is also what people do in practice. They say, well, let's explain 90 or 95%. Why? Yeah, that's why, right? I mean, that's if you do this as pre-processing for a regression task, then you can use your cross-validation, and now in a very simple way, right? And that to just determine, okay, with which pre-processing, so for how many principal components, and then running linear regression or classification or whatever you do, right? I mean, that's which number of principal components gives me the best performance. Cross-validation is always the right answer in these types of things. Yeah, PCA finds the global linear structure by definition, right? And that's good, that is great, that creates interpretability, like we just discussed. However, if you force something to be linear and the data is not truly linear, because the low-dimensional manifold is not strictly linear, like, for example, here, right? In this data, we have essentially 3 clusters. We have blue, we have orange, and we have green, right? Of very different sizes. And the first principal component here is exactly on the slope of the orange cluster. So, okay, great, right? I mean, that indeed explains a lot of the variance in the data. Not all, but a lot. If we project the data down onto the first principal component, we have it here at the bottom right, you see that the blue and green points that were perfectly well separable in the original space, right? You could very easily draw a circle around them. All of a sudden, yeah, they're just mixed with all the rest of the stuff. Getting that out again is tricky, right? Basically, you painted yourself into a corner. PCA painted itself into a corner, right? So hence, you always need to be aware that with data analysis techniques, both supervised and unsupervised, you're putting a lot of your own beliefs of how the data generating mechanism works onto the data. You're sort of shoehorning it in, right? PCA is linear, which works great if the data is linear or linear-ish. But at the moment it's not. Is that a bottle of whiskey? Please say yes. Actually, if you would have said yes, I would have been worried. But that looks like a very nice bottle from here. No, just schnapps. Good. Okay. Yeah. So here you can already see that this can be a problem, right? I mean so if there's different structures in the data and you shoehorn something linear in, that is not going to be great. Just looking at the variance is not going to be great. Instead, here it would help if we would maintain the distances between points. Or the opposite, if we make sure that those points that are far away from other points, that they stay far away, right? And the twain shall never meet. So, which is a perfect segue to salmon mapping. We already discussed, hey, the one was great, the other was also great, and they also both kind of sucked. But this is the idea of salmon mapping. We're not going to shoehorn a linear model onto the data, which was already a bad idea. Previous example, and on the whirl even more so. But now we want to make sure that the different colored clusters, right, even if we don't know the clusters, that they remain sufficiently separated. And then on this data, you get this output. Salmon mapping is a variant of multidimensional scaling. So around the time when this was invented, late 60s, early 70s, there's at least 3, 4, 5 different proposals which are mathematically not identical, but the ideas behind it, there are. What is the idea? It's very simple. We have some high dimensional data, right, P features, and we want to now project it into a lower dimensional space, K features, right, K dimensions. So in a space of R to the power K. These are our data points that we have, and we want to now project these data points, we have n data points in P-dimensional space, into, we want to basically relabel them, so each data point we now have a Z, and this needs to live in K-dimensional space. And what we now want to minimize is called a stress function. Different variants. So Kruskal-Shepard is essentially minimizing least squares. These squares you know, you love, or you hate. But, essentially what we have, we sum for every pair of data points, excluding if they're identical, of course, then it's just the distance is defined as 0. And what we do, we measure the distance between the two data points as they are, and so in the input space, right? I mean and it can be a Euclidean distance. That can be, well, any distance measure that you like, right? I mean but let's just simply do square distance here, and then we look what is now the distance in the embedded space between these two data points, and we take the square of that, and that we want to minimize. So it's very simple least squares, right? You already see that if we now allow K to be P, right, exactly the same, then you just get basically what comes in comes out, right? And the moment I allow you fewer dimensions, right, I allow you less wiggle room, well, then you try to essentially squeeze out, right, those dimensions where data points are very similar in distance. You try to sort of merge that, and that's essentially what you're trying to do with Kruskal-Shepard. Salmon mapping rewrites this statement ever so slightly by, look, here we have exactly the same thing as we had here in the sum, except that we normalize it now by the distance. What is there? The key point, you want to emphasize the smaller distances. Things that are really close, you want to keep really close. You don't want to sort of let them all of a sudden be pulled apart, right? And that's what salmon mapping emphasizes over standard Kruskal-Shepard. If I would now stop talking for 15 minutes, I'm pretty certain each of you can come up with at least 2 other formulations that also make sense in certain ways, right? Maybe you just flip it around. Maybe you want to emphasize the longer distances, right? I mean, things that are far away should really stay far, and so on and so forth. It's easy to come up with all sorts of variants. I see that actually on this slide, I should have put my green cross, because the actual details for salmon mapping you will find in the ESL book. So the Introduction to Statistical Learning with Python book gives a bit little detail on these things. So for this chapter, you need to look really mostly at ESL. Okay. Now, how do we compute this? It's very straightforward in that we measure first the similarities in the real data, right? I mean, mind you, that is actually quite a beast already. If I give you 10 data points, you need to measure 10 pairwise all distances, right? So this is roughly n squared. If I give you 1,000 data points or 1,000,000 data points, at one moment you're going to say, okay, please no, right? So similarities, pre-computing similarities, and this is also a little bit, just to cut back to your, do we want to use kernels, yes or no, right? And that's, if you want to compute the gram matrix, kernel methods are good for modest amounts of data, but, generally, even though we have all sorts of smart tricks to speed things up under certain assumptions, but you don't want to have too large similarity matrices. You can kind of see this as a kernel trick again, right? And that's, we just look at the, we center data points. Centering is something we do with PCA, with all sorts of these methods, because otherwise, if you don't center, then the scale of your data may affect the output, even though qualitatively it doesn't matter. So okay, we center things, and what we then do, we simply compute, or we minimize in gradient descent step by step. We tune basically the positioning of these z values such that we overall minimize the square distances. Yeah. Oh, I don't know what is up with my laptop. I started talking about maybe buying a new one. I think it heard that. So if you have similarities as centered in the products, then salmon and PCA are essentially the same. So that's a very special case. Good. MDS, as we just saw it, you need similarities, and then, well, gradient descent, so basically move things around such that you minimize the values. Now, and you can forget about the point coordinates. So this can be tricky. If you have a modest amount of data, but this data is very high dimensional, this is a good thing, because you just have to compute the similarity metrics, and then you can forget about your very wide table, right, for the time being, and effectively you operate on a much smaller data set. However, if you have many data points, then, well, at one moment it starts to blow up. You have a number of smart tricks where you can also just try to minimize the ranks. So you just need to compute how far away are points from each other, and that's the only thing that you want to maintain. Essentially, a rank statistic variant. Not super important. And this is going to be not part of the exam, that I'm going to promise you. So the rank-based one. Let's see if this now works, and where it works, or why we need actually something in addition. Here we have some data of genomes of influenza. I mean, it's winter, so it's influenza flu season. In this particular case, only 79 dimensions, but 79 is already cursor dimensionality land, right? If you want to cluster this with the standard algorithm, there. We're going to discuss this next week. So now, using the approach that we just saw, but with random starting solutions, right? So Gillis disapproves. Multiple runs of gradient descent. At one moment, you get some results which are stable, which you like, right? I mean, that you have here one on the right-hand side that was published in Science, so at least the scientists, they enjoyed this one. And what you can then see, right, that after the fact, after getting this, they started to investigate what are these clusters that you now see, right? Which these are clustered together in salmon projection, because in the high dimensional space, they're also relatively close together, right? That's just the interpretation of seeing a cluster here means that there is a cluster in the high dimensional space. by looking into this, they could find all different strains of influenza that indeed are genetically related. So, okay, pretty nice, right? I mean, that you run randomized algorithm a number of times, you pick that visualization that you like best, you analyze it, and you have a science paper. What says here? The level of increase of stress function with decreasing K can point to the dimensionality of the data. This is a very strong statement. What is meant here is that if you were to do some form of cross-validation, basically look for different values of K, how much stress is there left, basically how much of the distances between the actual points can you not explain in your lower dimensional space, right? So that is basically the error that you make, you could say. That in this particular case, people argue this shows what is now the intrinsic dimensionality of the data. If you can maintain all the distances with only a handful of features, right, I mean these sets, then, well, the data actually lives in a, let's say, 5-dimensional space. And I'm a bit more cautious there, a bit more cautious. But that's, I mean, purely mathematically, they have a point. But in the real world, is doesn't always agree. This is a statement that I do agree with. In many real-world cases, there is sort of a ballpark of a reasonable number of features, all of which it doesn't really matter so much. And whether this data is now 2, 3, 4, or 5-dimensional, I mean, I didn't look at the plots for this particular one. It's hard to say, but yeah, this is roughly the dimensionality of the data. In that ballpark it lives. Good. Third method, and then we're going to be done. Disney. Disney, we take one step beyond salmon mapping, but before I can show what this step is and why it actually is a very good idea, why that these authors came up with, I need to show you what happens if you don't use their smart trick. I first need to explain you SNE. SNE is stochastic neighborhood embedding, and it's actually called SNE because the other one is called Disney. What we have, what we want, right? What we're after right now. I mean, almost all the math is gone. It's going to be just pictures, large part. We have data. Data is high dimensional, and what we want a low dimensional embedding. Could be 2 dimensions, can be 3, can be 4, can be, but generally we're interested in 2. But the method, just like salmon mapping, you can choose essentially an arbitrary number of dimensions, just that 2 makes most sense. Now for both, so suppose that we now have this low dimensional embedding, right? I mean, that's it's magically given. Now in both, we can compute the distance metrics. Between every pair of points, we compute what is the distance, right, in the original space, in the down projected space. We can use this, we can do this purely linearly, we can do this in whatever distance metric that you're interested in. But what we can now do, because up till now, this is essentially the same thing as we were trying to do with salmon mapping, right? Essentially with salmon mapping, we tried to make sure that these two are as close to each other as possible, right? We want to find that set where these distance metrics, matrices are as similar as possible, right? I mean, that's under squared loss. Now in SNE, they say, okay, well, actually, do we really, truly care about the exact distances? No. What we care about, if something is close, it should be close. If it's far, it should be far, right? But do we really care that the distance should be 0.1 in both spaces? No. If it's 0.9 here and 0.7 there, or this is all fine. It's all fine. So rather than looking at the exact match between those, what we should do is we should actually look at the distribution of distances for each point. And we should make sure that those stay the same. Okay. I'm going to explain this step by step. We have the step where we're going to go up, 2, and then 3. First distances, then we can look at what is the distribution of distances for an individual point. Then we can think about how does this now look in a low dimensional embedding. And then we can see, and we can explain, how do we now make sure that we have, so because this part here is just given, right? Basically the data gives this, up to some mathematical choices. Then we want to find, in the end, an embedding that makes this similar, that requires us to know how do we compute this to begin with, and how do we determine similarity. This is in the original input space. Imaginary, of course, right? I somehow projected this down to 2 dimensions, right? I mean, that's just, otherwise, none of you can visualize it, and me neither. We're interested here at point xi, right? So the yellow one. And what I now plotted here are some of its closest neighbors. Those are the black dots, right? What are the concentric circles? Those are, if I now draw a Gaussian around it with a certain variance, right? So these are basically the probability mass, right? So you have your bell curve over it. So around point xi, I have the distribution pi, which is normally distributed, centered around xi with some variance. How I choose this thing, we'll see in a second. But, I'm now able to compute under this distribution for each of these xj's, for each of these points, what is their probability under, well, this Gaussian, right, under these circles. That's what I have here. This is the probability of a point j, given that I'm actually currently at point I, right? And I have this variance of I, which essentially is just the exponential, the actual distance squared between them, standard deviation, there we are, right? I mean, that's so standard stuff. That we can compute the probability of xj. Essentially, the closer xj is to xi, the higher this probability, right, under this. Now, of course, if I now tweak this sigma, if I tweak the variance, I can basically squash this big set of concentric circles down. It widens out much more, right? I mean, and I give more probability mass to points further away. Why would I want to do that? Well, let's now move our focus from point xi to point xi, but now at the bottom, right? And that's, if you now were to use the same variance as I just did, I would get this set of concentric circles, exactly the same, right? That's, but within the neighborhood of this new xi, there are not so many neighbors that close by. So if we were now to try to maintain the probabilities of seeing a neighbor at a certain distance roughly the same for all the points, this is a very bad variance, because all the action is in these barely visible circles, so it just has very low probability neighbors far away, right? And that's, whereas actually for xi, they are further away, but these are its closest neighbors. So what we actually should do, we should widen these concentric circles for this xj, or for this xi, sorry, right? Such that, whoops, we again get a somewhat similar-ish distribution of the k closest points to the query point, to xi, right? So essentially what we're now going to be doing, conceptually, for each data point, we want to now determine what is that variance, such that if I now look at the conditional probabilities of the k closest points, that those distributions are roughly the same. So for the xi we just had, here a small variance is fine, because then I have xj is quite close by, this is a bit medium distance, medium-ish distance, a bit further away. And for this one, I need to change the variance such that this one is now reasonably close by, and so on and so forth. I'm going to do this for all the points. And of course, each of these distributions are going to look somewhat different, right? They're not the same, but I'm going to be tuning this variance such that they become similar-ish, right? So, why do we want to do this? Why do we want to change this variance? Such that for each data point, for each xi, we know that there are some neighbors that receive sufficient probability mass such that we can actually say, okay, well, there is a neighbor with some probability close by, right? And that, essentially, we say there do not exist complete outliers in the data. That's kind of the hidden assumption. Good. This is the first ingredient that we need. Is this somewhat clear? Essentially, we don't care about the exact distances between points anymore. We now care about constructing a conditional probability. So for each data point, there's a conditional probability distribution, such that essentially stochastically, if we were to generate data points from that distribution, you would, with reasonably high likelihood, generate, well, in this case, these 4 points. For the other xi, the other points, right? You get the points roughly, the densities are sort of captured. Okay, now we're at point 2. So this was the left-hand side, now we're on the right-hand side of the two things, and then we're going to connect them. Now we're in the low-dimensional space, right? The one that we want to find, that we don't have. What do we have there? Well, the original idea of SNE is that, hey, for a query point, Zi, we're going to construct a distribution, Q, this should just be Q of J, which is again going to be a normal distributed, centered around itself. And now the variance is not a parameter, but we fix it. Why do we fix it? Well, because we have a fixed dimensionality of the low embedded space, and we don't want to have too many degrees of freedom. We just want to have a somewhat interpretable degree of freedom, this variance is in the original space, because there we know essentially what is the, let's say, the attention span around a data point, to where do we want to look, and in the embedded space, this parameter loses its interpretation. So the moment that we have this normal distribution, then we have again concentric circles just like here, and we can again compute the conditional probability just like that. I mean, this is quite straightforward. We do this again for each data point, right? It gives us conceptually a distribution. This means that we have this right now. We have on the left-hand side what we just discussed. On the right-hand side, same thing. For the same xi, this is now projected into zi. Note that you can see that even though somewhat similar, so there is a close point here and a close point here, and this one here is a bit closer in the embedded space than it's here, but the embedded space is quite close to the left, but not exact. And we don't care about the exact distances. We only care about that these two distributions, this distance distribution at the bottom, that those are similar. That's what we care about, right? And that's what we have then here. So as you can see, this is Gaussian, right? I mean, these are the probabilities. So like this one has a very high probability, lower, and so on and so forth. And the same thing over here. Okay, now this is for one data point. We're going to do this for every data point. So for every data point, we have a curve on the left and a curve on the right. And what we now want to find is that embedding, so that positioning of all the points Zi, right? Whoops. Such that this entire stack of things is maximally close to each other. So this means that we need to compute, we need somehow to determine how different or how similar is the yellow curve to the blue curve, right? And then compute this for all, sum this, do something magical to it, and there we are. What we're going to use is the KL divergence, this Kullback-Leibler divergence. Some of you may have already heard about this in other courses. We skirted by it earlier in EML. Kullback-Leibler is a definition based on Shannon entropy, based on mutual information, amongst others, that measures how far apart, how different are two distributions. And it measures this in terms of bits. It's an information theoretic measure. It's one of the reasons why I love it. How can you define? There's many ways to define it. So CI is the comparison. This is how you write it. This is the source distribution, the presumed true distribution. And this is the query distribution, right? So the one that we want to compare against. And what we now measure is, well, so if those two are exactly the same, the divergence will be 0. How can we measure it? We can rewrite this thing. In the end, we end up in the right-hand side. But one way is to measure the entropy between the joint entropy of the two distributions minus the entropy of the one distribution. What does this mean? Here, I need the number of bits, or I mean, here I measure the number of bits to encode a data point under just P. And here, it's actually, this should be a bar. This should be a bar. This is the number of bits that I need to encode a data point under distribution P. So that's basically the minimum number of bits, because that's the presumed true distribution, right? And that's also what we now defined as the true distribution, right? And here we have if I now tell you first, what does Q predict? How many bits do you then still need to predict P? Now, if Q is perfect, if Q is the same thing as P, you don't need anything, right? However, if Q is a bit stupid, if it makes a mistake here and there, well, you need to fix it. The more stupid Q is, the more fixing you need. Every fix costs bits that we can measure, right? And that's basically how much red ink does need to be spilled when we correct the homeworks of Q. That's essentially what this comes down to. Now this you can write out as a sum for every pair of points, where we look at what is the probability of a point J given I. So this is so basically what is the probability of a point J in the neighborhood of point I, right? I mean and we do this for all J's. And then we take the product. What is now the relative entropy here? Is a logarithm to base 2. This is the conditional probability, the same one as we have here. And we divide this now by what is the probability that Q assigns for the same pair of points. And there you can already see if Q assigns the same probability mass as P does, well, it's just one, or basically it reduces to 1. Logarithm of 1 becomes 0. There you are, right? I mean, so then we don't need any additional bits. If Q assigns too high a probability compared to P, well, then this term starts to grow, right? I mean, you take a logarithm to base 2, that's a larger number of bits. And exactly the same thing happens, because it's symmetric, if Q assigns too low a probability mass. So basically you get a penalty either way. You can also see that if Q assigns 0 probability mass, then we have a problem, right? We have a division by 0, and then KL divergence cannot be computed. So that's something we need to avoid. Good. What we have, if we avoid this, that KL will be larger or equal than 0 for any pair of distributions, and it will be 0 if and only if they are the same. That's the nice thing, right? So it's an ultimate way to determine divergence. It is asymmetric, however. So if I assume that P is the true distribution, then I get how many bits do I lose if I use Q instead. But if I flip it around, if I assume Q to be the right one, and how many bits do I lose if I now use P, you don't get the same values. Doesn't matter in our case, because we have one rightfully assumed to be true, namely the true data, such that we can now fiddle with the blue distribution, the Q one, the embedded one. That's the one that we can change. So there we really want to reduce the divergence between the two. Yeah, exactly. Which means that in our case, we have a large penalty when Q is small for large P, and then, well, the vice versa, that doesn't matter here. This is nice to know, but not so important right now. Good. What we did, we went with PCA from maintaining variances to salmon mapping, maintaining distances, to right now maintaining probability of seeing a neighbor at a certain distance, right? That's essentially what we transformed from the one to the other. So that's what these conditional probabilities that we construct. Say, Pj given I is the probability that a data point xi really wants a neighboring data point j at a certain distance. Recall again, we had these variances, right? The smaller these variances, the more urgently xi wants to have neighbors really close by. And if this variance is really relaxed, it's like, okay, well, I want a neighbor somewhere. I don't care. And now the asymmetry of KL divergence, of like a large discrepancy between low and high values, that starts to kick in. So if we have a low variance around the query point xi, then what we really want is a distribution Q that also squishes data points close by. Otherwise, we suffer a huge penalty. And that creates a very nice tension that creates good embeddings. And these variances are picked such that each point has approximately the same number of neighbors. This is a literal quote from the paper, right? I mean, so this is a bit black magic, and cross-validation for a change is not the answer. Good. Yeah, how do we learn these things? I mean, gradient descent. Gradient descent. I mean, that's I have to admit, I've never even implemented SNE myself, so I'm not going to require this of you in the exam either, right? That's gradient descent. What should you always keep in mind when gradient descent is the answer or part of the answer? It's stochastic. It's not deterministic. So it's an algorithm that I do not like, because you and you and you will all get different outcomes every time you run it, right? That's, so you need to run it multiple times and see whether you like it or not. Here's an example of why SNE is not in use anymore, why we need to go to TISNE. This is the true cluster, the clustering structure of some data set in 10 dimensions. If you, like in 10 dimensions, if you properly project it down, right? That, if we now apply SNE, what you get is this. It's not bad, but if I would not have given you the colors, or those of you who are colorblind are now at the advantage, in the left one, you can kind of see that there's different clusters, right? They're sort of separated. In the right one, not quite. I mean, this blue blob over here is somewhat separated-ish, and here there is a bit of a border area, but these three clusters are merged together. Why? There's no reason. It's just by the mathematical definition, right? That this is called the crowding problem. SNE, stochastic neighborhood embedding, is a very cool idea, but it tends to put points closer together than you strictly want them, right? I mean, it really what really wants to create crowds. It's relatively easy to see. Suppose that we now have here the an example on the left, and we measure just the distances between each of these pair of points. So this is a distance of 1, distance of 1, distance of square 2. Standard Pythagoras. Which distance should we now preserve if we project this high dimensional, this two-dimensional thing onto one dimension? Should we maintain the longer distances, or should we make sure that the distance between green and blue is short? And what SNE essentially favors is this one. So pulls everything a bit too close to each other. Where does this come from? We see this in a minute again. So we can see this from how can we solve this. This is the, okay, my animation is a little bit borked right now because this definitely should not have happened, but okay, good. The blue line is not yet here, right? You don't see the blue line. So we have here the black line, which you can see. This is your Gaussian distribution, right? And this is the Gaussian distribution in our case, both in the original space and in the embedded space, right? Now, Gaussians are great because they have one mode and a mean and whatever, right? And they drop off quite quickly. They are reasonably heavy-tailed in the sense that they never truly hit zero. But at the same time, they're also quite weak-tailed. If you now compare the black line with the blue line, now you can see it, you can see that the blue line, it has a lower peak, fine, but its tail, it will take much, much, much longer before it finally gets close to zero. It will also never hit zero, right? Now, what does this now mean is that for the black line, if for this data point, for example, right, for the blue point, this is the black point, this is the blue point. If we want to maintain this distance, we really have to put it here, because the moment I move it a bit to the left, then I assign it actually way too much probability mass, right? Because it's quite steep here. This is basically the pivot point. Here, it's way too low. So I really, really want to have blue here. Whereas for the blue line, at the same, let's say, same similarity, right? The optimal value is here, but it is so flat here already that if I now move it a bit to the left or a bit to the right, we can be honey badger about it. We really don't care. We really don't care where we put it. So effectively, by relaxing our distribution, this is not a technical term, mind you, but by relaxing our distribution, by pulling it down a little bit, by reducing this slope, we can actually allow the algorithm to, well, also create a bit of air in the embeddings. And now we go from basically saying bye-bye to the Gaussian in the embedded space. And instead, we take a slightly more relaxed distribution, and relaxed, the technical term is one with heavier tails. And that's the t-distribution. You can also have chosen a Weibull or something else, so it doesn't really matter. You can plug in all sorts of things. But we have to replace, in the embedded space, the Gaussian with a heavier tail distribution, and then magic happens. So Q needs to be low dimensional, or it needs to be t-distributed, so bloop, like that. And then we have t-distributed stochastic neighborhood embedding, or TISNE for short. There are a few minor other changes. You can study this at your own leisure. This is, again, not going to be part of the exam. I'm going to just quickly show you another interpretation of what TISNE is now actually doing compared to SNE. So we want to maintain, effectively, the neighborhood graph. This is what our goal is, right? So we want to maintain, we get an embedding such that the blue points, right? So this is the similarity metrics. And if we were to look at these values, these should be low, these should be low, and these should be low. And for the white ones, we don't really care, right? High, whatever, right? We don't care, we don't. But the low ones should be low. And what we now get is that for SNE, so high dimensional data, we have these nice clusters. But for low dimensional data, it can very easily happen that it starts to over-focus so much on where things need to be exactly, because it incurs such a high penalty because of the slope of the Gaussian, that you get the neighborhood graph that looks just like a mess. That's what happens with SNE. And if you now, whoops, where are we? Yeah, okay. So, and if you use TISNE, then actually, wait, my animate, I have no idea what's going on with my laptop. Something is going on, not good. Anyway, with TISNE, you do get proper things. It's really, animations board, it keeps flashing. I think it's time for a new laptop. Yeah, already mentioned with kernel trick, creating a gram matrix. It's also basically, I need to consider every pair of points. It's very painfully computationally. Same thing if you compute SNE or TISNE, like in a vanilla type of in a naive way, right? So effectively, what many implementations do is that you just look at the k nearest neighbors. I've already been saying this quite a few times, right? Now, you might ask, what is the optimal value of k? And then the answer is cross-validation, or you just choose a reasonable number. But mind you, we now need to choose k for what to compute, and we need to choose this variance to include a certain k number. These are two different parameters, and we have a stochastic algorithm. This is tricky. I'm almost done. I'm just going to show you that this actually works. This is a TISNE embedding of, well, yeah, word associations, basically which words happen in what. Word embeddings, these days we compute, ChatGPT also has its word embeddings, word embedding. There is now a whole arsenal of methods to compute really good word embeddings beyond what TISNE can do, but it's a nice visualization of what TISNE can do. So what you see here is that, well, let's see, where do we have some clusters? Popeye, spinach, cartoon, stalk, corn, scarecrow. There's a cluster here, sow, reap, harvest. Yeah, arguably these are three clusters of words that are syntactically very different, right? Semantically, well, also technically different, but at the same time, quite close to each other, right? So by just seeing how close these words are in texts, doing a TISNE embedding, you actually can learn something about, in this case, language. Can we go further than that? Well, yes. This, you really need to look at the slide. You can't see it right now. I mean, this is not good for your eyes. This is for movies. Do we have certain subclusters of movies? I mean, or what are now the, let's say, if you like a certain set of movies, what are the best ones to watch next? You can use TISNE embeddings or other embedding-based techniques for that. Mouse brain cells. As you can see, it doesn't have the crowding problem as badly as the previous example. Whether these are now perfectly separated into clusters, no, but this really does indicate, and this is what's marked here with colors, different types of cells that we know are similar in type of cancer, right? So it gives some insight in how many subtypes there are. Does it also work with images or with any data? Yes. And that is why, I mean, it's not the ultimate algorithm. I'm not going to backtrace there. But if you have high dimensional data, t-SNE is a very nice technique to boil it down to its essence and get a bit of insight. You need to be careful because, as I say here, so it's essentially the current standard or state of the art. People are using it to gain insight into deep neural networks. The crowding problem that I spoke about, it's reduced, it's not gone, right? The mouse cancer example just showed that it's better, but it's not solved. So maybe a nice bachelor's thesis, master's thesis, or maybe a PhD. With these stochastic type of methods, you always have to be a bit careful because maybe you got lucky, maybe you got unlucky. And just like with PCA, where we impose a linear transformation on our data, and that's what we want to find, and of course that's what we're going to get. And if it doesn't exist and we just get something meaningless, also with t-SNE, we can be duped because we, again, force certain distributions and certain assumptions. And if you don't make this very explicit and know what you're doing, yeah, the results can be arbitrary. So the number of clusters that you get, the sizes of the clusters, the densities of the clusters, the distances between clusters, in a t-SNE embedding, those are essentially meaningless. And you need to be aware of that, right? So going back to the fact that this yellow cluster and that green cluster are now far away doesn't mean anything. Or maybe it does. That is not to be said, right? What you can say is that these data points, they share some structure. That you can say. But there is no saying maybe this is a very widely spread cluster, maybe this is a very compact cluster. You can't say. You really can't say. t-SNE is not meant to show this. Good. Yeah, sensitive to hyperparameters. If you have more than 3 dimensions, basically if you want to project it into more than 3 dimensions, t-SNE is a bad idea. KL divergence starts to become difficult to compute. Random noise does not always look random. So if you have random input, you do t-SNE, you might get a pretty picture. Is that a good or a bad thing? Well, it depends, right? It's a bit like if you suppose you're swooping around with a super sharp katana. Yeah, okay, you might hit and slice some things. Is this now the katana's fault or your fault, right? I mean, t-SNE is a katana. I'm playing Cyberpunk right now, so that's why I'm thinking of katanas. Yeah, it was so random that I needed to explain this. Yeah, good. And one other thing, and this I find still. This is something I would like to play with a little bit. If you've now found a t-SNE embedding and you have new data and you would like to see where in the t-SNE space does my new data live, right? I mean, a wild new mouse appeared, right? And where does this go? No, can't be done. There's no straightforward way of seeing where in the embedding does the new data, because the embedding was really found to minimize essentially the stress function, right? These distributions over the data points we already had. So a wild new data point can screw up everything. And this is annoying. It annoys the hell out of me. So I would like to come up with an embedding technique where you can add more data in a meaningful way. One approach, I'm not going to even mention it beyond its name, UMAP is a popular alternative to t-SNE. Mathematically very different, the results are very similar. Good. This will be just clickable on the slides, that you can play around with t-SNE a bit yourself. Let's sum up. High dimensional data is very challenging, and we're basically cursed the moment we have too much data. Dimensionality reduction, and we saw 3 techniques today, PCA, salmon mapping, t-SNE, to reduce it into a very small set of dimensions, or an embedding. In this embedding, we primarily focus at looking at it, such that we can gain some structure of the data, some insight. But you can also use this low dimensional embedding for some downstream task. Then you can cluster, then you can learn your decision tree, all things that we will discuss later. PCA is linear, MDS, salmon mapping, preserves distances, t-SNE preserves distributions of distances. Those are the 3 things that are most important of today's lecture. And on that, I want to say thank you very much for your attention. See you next week.